So our agenda is, first thing is, I will introduce Cortex-M4 based controller. Followed by that, I will talk about Cortex-M4 specific debug and trace features. And the third thing is I will talk about how to do winIDEA configuration for debug and trace. And I will be giving live demo with different use cases. Here I have written one of the use cases is OS tasks ISR runnable profiling. And at the end, I will conclude this webinar. Moving to the next slide, this is Cortex-M4 CoreSight Architecture. So I'll start speaking to a point, how do you access the chip by the debugger? And the answer is either through the JTAG or SWD interface. Beneath that, we see access ports. So what they do, access ports allows us to access on-chip resources such as peripherals or memory via the system bus. In addition to that, we have debug and trace modules. Basically, these debug and trace modules are called ARM CoreSight IPs. So what does the manufacturer of a microcontroller do? They integrate this Cortex-M4 with the required debug and trace modules in order to make a complete CPU subsystem. Now moving to the modules such as run, control and breakpoint, what they do. Basically they control the instruction execution of the core. In other words, they bring functionality such as run, halt, instruction stepping, or instruction breakpoints. Now moving to the trace modules, ETM, embedded trace microcells, DWT, data watchpoint and trace, instruction trace microcell. Basically these modules generates trace data which goes through the TPIU trace port interface unit to the output port. In most of the Cortex M4 based microcontroller, we have two types of output ports. One is parallel and the second one is called SWO, that is serial wire output. Moving forward to the next slide, which is Cortex-M4 Trace architecture. So the name itself says we are going to focus on M4 Trace architectural concepts. So first I will talk about ETM, embedded trace macrocell, which provides instruction trace. What it does, it captures Cortex-M4 program flow, then it creates instruction trace messages which goes to TPIU. Now I will talk about DWT, data watchpoint and trace. It's shared between debug and trace system. Question comes how? DWT module has 4 hardware comparators which can be served either as data access breakpoints or trace on-off triggers. So in general, DWT trace data being forwarded to ITM where trace messages are being generated and then it goes to TPIU. Just now, few seconds back, I have said DWT comparators can be used as trace on-off triggers. What does it mean? It means DWT hardware comparators can be worked in conjunction with ETM to confine the program flow trace. A use case I will be showing in the later part of this webinar so that it will be more clear to you. So you have to just be patient as of now. Now I will talk about ITM, instrumentation trace macrocell. This module can generate trace messages by itself. In software, you can directly write to the ITM stimulus ports which can generate trace messages and it goes to TPIU. Now I will talk about this TPIU module. Actually, it receives trace messages from all the input sources and outputs them by two types of output port. First one is parallel, which has either 1 or 2 or 4 data pin and one clock pin, which is also called SWO, which is an asynchronous pin port. Now talking about the advantage and disadvantage of this parallel trace capture method and SWO trace capture method, which I will be discussing in the later part of this webinar, so you have to excuse me as of now. Now talking about ARM CoreSight generic debug connectors. So there are two connectors we do see here. First one is 10 pin connector and the other one is 20 pin connector. With 10 pin connector only SWO trace is possible, while with 20 pin connector we can perform both SWO trace and parallel trace. One thing we have to look here is SWO trace pin is shared with JTAG TDO. So both SWO and JTAG cannot be used at the same time. That's why Cortex-M4 offers another additional debug interface which is called SWD, serial wide debug. Actually, SWD only used the JTAG pins such as TDI, TMS, and TCK. Thus, the JTAG TDO pin may be used as SWO pin. Apart from that, one additional thing we have to look for is in parallel trace capture method, these parallel ports are often multiplexed with other IO pin functions. So it must be checked whether these pins can be used for parallel trace or already used by the applications such as timers or SPI. For more flexibility, most controller offers multiple options for multiplexing the parallel port pins to avoid the conflict with application IO functions. With this slide, I want to give you an introduction what happens when a debugger like winIDEA connects to a Cortex-M4 based controller. So I will distinguish three different scenarios for establishing a connection. First one is a new debug connection. Second will be a connection to the target not only for debugging but also for flash programming. And the third one is a reattach to the target. This may occur after a system reset or after exit from a power saving mode. The exact sequence for the new debug connection heavily depends on the controller type, but most of the time it remains the same. So talking about this, connection to a target is typically starts with asserting a reset. Example, by asserting the reset pin. This typically resets the M4 core and other modules except for the debug related modules such as JTAG, access ports, or run control logic. Then, based on the setting in winIDEA, the debug port either remains in full JTAG mode or it is switched to SWD mode. The debugger only uses the dedicated JTAG pins TCK and TMS for this selection. Followed by that, halt on release from reset functionality in the core gets enabled to make sure that M4 core immediately enters debug halt mode after releasing from reset. Once the M4 core is out of reset and in debug halt mode, the debugger can connect to it. Example, read out core registers. Talking about this RAM ECC protection. So RAM ECC protection scheme of some controllers also requires that the debugger first initializes that is writes to all RAM location in order to generate a valid ECC before reading from a RAM. Now talking about this watchdog, so most controller targeted to automotive market feature an on-chip watchdog timer which is enabled after reset. So the debugger also needs to disable the watchdog before its time expires. Otherwise, device will reset again after a while. Now discussing about secure device. So at a specific points within this sequence, the debugger may also check if the device is currently secured. Example, a flash protection is active. The user may then optionally disable such protections. Example, by performing the flash mask erase. Now talking about the second scenario where not only debug is required but flash programming is also required. So in this case we need some additional configuration. Actually, the flash programming is typically done by a so-called programming monitor routine executing from on-chip RAM. As writing and executing from on-chip RAM is sometimes prohibited as per default, example by could be a memory protection unit. So in this case, such protection settings also need to be disabled first. Now talking about the third scenario, that is reattach. So it means connecting a debugger to a target which has already an ongoing debug session. This is also called hot attach. This situation happens for an instance if the controller goes through a reset cycle or wakes up from a power saving mode. However, it assumes that debug logic of the chip remains active. I mean, it is not reset or not powered down. A debugger in any case, the debugger will permanently pose the status of the target. So whenever the target or part of the target is not accessible, and suppose in power saving mode code is not accessible, then debugger will detect this and report this status to winIDEA. Now the debugger keeps polling to the target, and once it has returned to active state, the debugger detects this again. And now what happens? The debugger can reattach to the target and either halt the CPU or just report the target is in same running state again. Suppose in case debug logic is not reset, then your previously set breakpoints will remain active and debug session will simply continues as it was happening before. So these were the three situations to establish a connection. Now the next slide is debug and breakpoints. So now we know we have two debug interface, JTAG and SWD. Talking about breakpoints, then we have 6 hardware instruction breakpoints and 4 data access breakpoints. And now talking about DWT, then already I have discussed about this module and the same concept is written here in words. Now the next slide is fault and exceptions debug. From this slide onwards, I will be spending more time on winIDEA so that I can show you what I am doing, how I am doing, and what we can achieve through that. So in order to what happens, sometimes you will end up in some fault and exception debug and you do not know the root cause. So what has caused the problem, what sort of problem it is. So in order to find it out, we must debug it. So what I have done, I have taken a use case where I'm imposing or forcefully I'm imposing a precise bus fault error. Why precise? Because for debugging purpose it is good and program counter can tell us what exact instruction is causing the problem. If you are going for an imprecise one, then in that case your program counter does not tell that because your application keep writing to the right buffer and subsequent instructions are also being executed. But an imprecise error can be forced to precise one by disabling this write buffer. So now we go to the winIDEA and we see how we are going to debug fault and exception debug thing. So this is our winIDEA. So now first we are going to download our software. So here it is our ELF file. Now we are going to download it. Now we will run the software. So you see here in our watch window software is running. And now we are going to impose precise bus fault error. So I will write 1 to this variable. So we see here a bus fault error has occurred, but our CPU is still running. So, and we do not know what's happening in the background. So now what we do, we halt our core and we go for this disassembly window. So here this also does not give a correct idea about what has happened. So now how we are going to find it out? In this case, we are going to use it a Cortex-M4 feature which is halt and exceptions, and now we are going to enable that in our winIDEA. So we have to go to hardware and then CPU setup and then core 0, and now we are going to enable everything because as of now we do not know what sort of problem it is. So we have enabled everything. Now press OK. Now again we are going to download it. Now let's run it, and again we are imposing writing 1 to impose that. Now we see here our core has stopped and it has stopped to some other part of the disassembly. Now we are going to use the call stack window to find it out what exact instruction has caused the problem. So let's go to the call stack window. Here we see in runnable.c line number 245 at this address, this is causing the problem, and same address you can find it our program counter registers R15 here. Now we know if you go to this runnable.c file and then see this is the section up to create a bus fault error. Now we know what has caused the problem, but what sort of problem it is. In order to find that, we can use this winIDEA Cortex fault report plugin, and you can open that from here. Okay, so I have already opened it here, and if you see, then it tells us this is a bus fault, and if you just open it, then within that you can find it out. Okay, this is the precise error. So this is the way you should debug such type of exception and fault use cases. Now earlier what we have done, we have enabled everything, but now we know there is a bus error, so that you can remove rest of them and then you can press OK, and the same way you have to do it to find it out. So in this slide I'll be speaking about DWT Cycle Counter. So actually it is a 32-bit free running counter that counts CPU clock cycles. So this DWT cycle counter can be used to find it out the runtime of a specific function or a specific part of the code which you are interested in. So this can be implemented in two ways. First one is using the breakpoints and the second one is using the macros. The difference between these two are using breakpoints, so definitely your core will halt, and using the macros on the fly we will try to find it out the number of cycles executed, and then on the watch window it will be multiplied with your time period and you can see the runtime of a specific part of the code. So let's go to winIDEA and see how I'm gonna find it out the runtime using the DWT Cycle Counter. So this is our winIDEA, and right now first I will talk about using the breakpoint method and later on I will talk about using the macro. So let's first open this Cortex status, because here you see the cycle count value in this window you can see, and assume this is runnable R2 and we are interested into find out the runtime. So let's put a breakpoint at the start, a breakpoint at the end, and let's run our software. So here it stopped and again run and it stopped at the end. So it shows it took these many CPU clock cycles and total runtime is 4.929 milliseconds. So let's cross check it. So at the start clock cycle count is 0 and at the end again the same value. So using the breakpoint method, this is the way to find it out the runtime. Now let's talk about the second method using the macros. So already I have implemented in my software for my runnable R3. So here I am resetting the counter and at the end I will try to find out the number of cycles, and in the watch window here you see cycles is being multiplied with the time period, so it will give me the runtime. So now let's run the software and see how it is behaving. See, so on the fly you can see the runtime of runnable R3 using the macros. So these are the two methods how to use cycle counter to find out the runtime. So far I have discussed about Cortex-M4 architecture, trace architecture, debug and breakpoints, then advanced debug concepts such as exception and fault handling, followed by that DWT cycle counter. So from now this slide onwards, my main focus is on tracing and profiling. So now we know we have two type of trace capture method. First one is parallel and the second one is SWO. So I will start with parallel trace capture method. Then I will discuss few use cases and at the end I will discuss SWO with one use case. So now I will start with parallel trace capture method. So in parallel trace capture method, we know that parallel trace ports are often multiplexed with another pin functions. So if I talk about port selection, then you must check before using what is available on your side. So as an example, if I take Traveo 1M and 2M device, then winIDEA provides a wider different port selection scope, such as for data and clock you have these many options. In case of S32K148 you have these many options. So when I go for the winIDEA, then I will show you the other parallel trace capture method settings. But as of now, I will stop here and I will move to the next slide, which is our first use case with parallel trace capture method. So this is our first use case slide with parallel trace capture method is OS running tasks ISR profiling. Okay. Now the sample which I am going to use is S32K148 device with ETAS OS. And our aim is to trace and profiling OS task and ISR. And this is how our profiler timeline will look like. And on the right hand side on trace window, you can see the raw trace. So now let's go to winIDEA and I will show you how to do that. So this is our winIDEA, and first I'm gonna talk about the parallel trace capture method setting. So let's go to hardware, then CPU options, then SoC advanced, and here you define which port has been assigned for data and clock. So suppose for clock I have assigned PTC2, but you have options such as PTC, PTD16 as well. Now go to SoC, then you need to select here protocol. You can select either JTAG or SWD in case of parallel trace capture method. Now you need to select here trace capture method, so you definitely have to select here parallel, and then this width you need to select. So there are three options: 1 bit, 2 bit and 4 bit. I am going for 4 bit. The difference is only about the bandwidth, so you can go with 1 bit also, 2 bit also. So I'm going with 4-bit. So these are the settings required for parallel trace capture methods. Now I will talk about the settings required for our use case, that is OS tasks ISR profiling. So first we need to set up this operating system. So let's go to debug and then operating system. Then if you click here new, then you can create a new operating system for you. So here I'm using AutoSAR base sample. So I will select here OSEK AutoSAR, and then you can give a name here, something like AutoSAR, but I have already defined, so I'm not going to do that. I will cancel it, but I will show you the settings afterward. So you need to, if you double click on this, then you need to select here OT file, because I'm using ETASOS, so I need to select here OT, and then definitely you need to select the OT file from your directory. So I have already selected, so now I will cancel it. Now press OK, and then you need to check whether you have selected your ELF file or not. Then you press OK, and now you download the software. So you have downloaded the software, and now let's run it. Now you see in the watch window your software is running as well. Now the important part is to create the analyzer setting. So first you have to go here and create new analyzer configuration. So suppose I'm performing OS task and ISR. So based on your convenience, you can write some name like tasks, ISR, something like that. So as I have already created, so I'm not going to do that. And here you need to select here automatic. So let's cancel this, and I will select OS task and ISR. And now I will show you what further settings it needs. So let's click on this hammer to see the further settings. So first I will talk about this hardware. So you need to select here profiler. A few seconds later I will talk about this selection. So moving forward to the profiler part. Here you need to select OS objects. So let's click on this. Here you need to select task and ISR, because we are interested in to trace and profiler task and ISR. If you select this task, then you can see here this OS running tasks. So basically this is the variable defined in your OT file, and using this we will try to trace and profile the tasks. Similarly for ISR, the variable responsible is OS running ISR. So let's okay after selecting these two things. And now I will talk about this manual record configuration. So let's click on this. So you need to go here DWT core 0, and you need to define these two variables in this hardware comparators. So you need to select here right axis, and then if you press on this, then you can select here by typing. So you see here OS running task. In this way you can select this variable, and then here you need to define sample data value. In the similar fashion you can do it for OS running ISR as well. Now when I was discussing about DWT hardware comparators, then I said we have 4 hardware comparators, 0, 1, 2, 3. What happens? So ideally the situation is you can trace 4 variables at a time. But what happens when you want to trace more than 4 variables? In that case you can use ITM. So if you want to use ITM, then it has to be defined in your software, where you will be defining which stimulus port you're using for which variable and all. So right now that is not relevant. So here for our use case, we are using these two hardware comparators 0 and 1 for tasks and ISR. And definitely then you need to go to ITM, and you need to just enable this module, and now press OK, and then press OK. So we have already downloaded our software, and it is running now, and we have done our analyzer setting as well. So now let's run this. So here you see there are tasks: write code, eat pizza, order pizza, and you can see nice profile timeline for that, and similarly for the ISRs as well. If you want to see the raw trace window, then you need to click here, and I will just put it here. And on the right hand side in this trace window, you can see the raw data as well, raw trace data as well. So this is how you perform currently running OS tasks and ISR tracing and profiling. Moving to next slide, or the next use case, which is program flow trace and profiling. What is our aim here? Here our aim is to trace the instruction flow and profile the code of all active running functions, subfunctions, and other relevant activities. And this is our expected profiler timeline. So here you will see all the active or inactive running functions and everything along with these tasks and ISRs. So now let's move to winIDEA and I will show you how to do that. So this is our winIDEA, and the parallel trace capture method settings remains the same. The only one thing which I'm gonna do is I will create a new analyzer configuration for program flow trace. So let's click on this, then you can define a name and then select automatic and then press OK. Here I'm not gonna do that because already I have done. So I will press cancel and I will select this program flow trace analyzer configuration. So let's click on this hammer and go for hardware. Then you need to select this profiler. Coverage, I will not be speaking about this. I will tell you what is the use of this in the later part of this webinar. Now I will go for profiler. Then you need to select here code and then definitely OS objects by selecting these tasks and ISR. Then press OK. This is the button, or this is the option to restrict the recording time. So here I have restricted to 2 seconds. If you uncheck this, then you can do it for longer time. So I will press OK. My software is already running. So now let's run this. So this is the result actually. Here is your task and ISR, and here you see in the code part all the active functions. If you just select this button, then only active functions will be there. If you just uncheck it, then all active and inactive functions you can see. If something is blue here, then definitely within that something more is happening. So you can enlarge it and you can see it's happening. Now if you want to go for functions and sub functions, that also you can see. So suppose here in runnable R3, within that R3 func1 and function 2 is being called. So that also I can show you. So you just enlarge it and then you can see the function and subfunction call as well. So this is how you perform program flow trace, and on the right hand side you can see the raw trace data. Our next use case is program flow trace with DWT Trigger Control. In earlier part of my webinar, I have said DWT hardware comparators can be used as trace on-off triggers. So using this use case, I will show you how to do that. So I will use DWT hardware comparators to control the ETM trace or program flow trace. So now let's go to winIDEA and I will tell you how to do that. So this is our winIDEA, and I have already created an analyzer for this, so I will just select this. And now let's go further. You need to select here profiler as usual and here code. And now I will talk about this configuration. So let's click on this configure. First I'll explain DWT core 0. So you need to enable this, and suppose you want to trace only a specific function. You do not want to trace anything else. So here you need to select this instruction execution and then you define the function which you want to trace. So suppose here I have taken OS entry millisecond. So you need to go for function and then you can select here OS entry millisecond. So just double click on this and select OS entry millisecond. And then in the next comparator, you need to define, again select here instruction execution and then you select here the exit. And then these two things you need to define here, and then you need to go to this ETM core 0 and then here you see start and stop. So here you need to define start the trace when hardware comparator 0 condition is met. So you need to select here 0 and stop the trace when hardware comparator DWT hardware comparator 1 condition is met. So I have defined here and you need to press OK and then OK and you need to run this. So here you see based on your hardware comparator condition, it just fetched information about OS in millisecond task, and on the right hand side you see the raw trace of that particular function, what is happening within that. So this is the way you need to use ETM in conjunction with DWT, or you can use DWT hardware comparator method to control the program flow trace. Our next slide is coverage analysis. When I was performing program flow trace in parallel trace capture method, I have shown you I have selected coverage as well. So what is that about? Actually, when you perform program flow trace in parallel trace capture method, you can go for coverage analysis as well. Actually, winIDEA coverage analysis provides statement coverage, function coverage, call coverage, and object level conditional coverage. So let's go to winIDEA and I can show you if you have parallel trace capture method facility available and you perform program flow trace, then definitely you can go for coverage analysis, which can help you in find it out the dead code, or when you go for software testing. So in these things, these coverage analysis will help you. So now let's go to winIDEA and see how to do that. So this is our winIDEA, and I will select the use case for program flow trace, and here you need to select coverage only, rest remains the same, so press OK, and then let's run this. And now you need to go for this coverage statistics tab. I'll just put it here, and then you can see, suppose this is buswait.c file. So this file 48% has been executed, rest has not been executed. In runnable.c, 88% has been executed, rest part is not executed. If I go for code level, then you see if these are green, means this line has been executed. If there is some deviation here, then definitely some conditional statements are here. If this is red, then this part has not been executed. So this part is about bus fault error, and right now I have not imposed it. So this part has not been executed. So this is how you can perform code coverage analysis as well using the program flow trace performed in parallel trace capture method. Now I'm going to talk about SWO trace capture method. So earlier part of this webinar, I have said I will be discussing about advantage and disadvantage between parallel trace capture method and SWO trace capture method. So let's see it. So right now our winIDEA configuration has parallel trace capture method setting. So I will change it to SWO trace capture method setting. So first, one thing you need to do, you must select here SWD in case of SWO. I will change it to SWO. Then our core clock frequency is 112 megahertz. So I have written here, you need to define a pre-scaler in such a way that pre-scaler plus 1. If you divide clock by this, then clock divided by pre-scaler plus 1 should be less than or equal to 10 megahertz. So here 10 plus 1 is 11, and it will give me approximate 10 megahertz or so. So that's all the setting we need for SWO. Now we need to press OK, and our download is required after that. And let's run it. And now we try to perform the program flow trace as we did in parallel trace capture method successfully. So now let's run it. So immediately you see here error overflows in recording. It means SWO trace capture method has not enough bandwidth to perform program flow trace. It means the basic difference between these two trace capture methods is the bandwidth. So program flow trace can be performed with parallel trace capture method, while it cannot be performed with SWO trace capture method. So definitely when you go for SWO trace capture method, you have to be very specific what you want to trace, and you cannot trace everything as you did in parallel trace capture method. So as I have said, many devices have just SWO trace feature. Program flow trace is not feasible with SWO, but there are still few questions which are unanswered. The first question is, can we do OS task, ISR, trace and profiling with SWO? And the second question is, can we do runnable profiling too with SWO? So the answer is yes, OS task and ISR we can perform. And for the runnables, we need an additional concept which is code instrumentation using DWT data trace. What exactly it is? Actually, the concept is to mark the entry and exit, and every entry is marked with a unique data value, whereas exit is always zero. So now, before moving to the winIDEA, let's have a look to the next slide. So this is how we are going to do it. We will use our DWT hardware comparators. First comparator will be used for enable, the second for OS tasks, this is for OS ISRs, and I will be tracing one global data variable as well. So I will use one of the comparators for that. And this is how our profiler timeline we are expecting to look like. So now let's go to winIDEA and see how I'm gonna do that. Before moving to the analyzer setting, let's have a look at the code instrumentation concept used for runnables. So entry is marked with a unique data value IPF runnable R2, and exit is always used with or marked with 0. And these are the value I have defined in this file. So IPF runnable R1 is hex 10, R2 is hex 20, and so on. And exit is always 0. So now let's go and have a look at the analyzer setting. So already I have created an analyzer. I would recommend for every use case, create a new analyzer setting. So I have already created. So now let's have a look. Now you need to select here profiler, and then you need to go to this manual trigger configuration, go to DWT core 0. So first comparator is used for runnable. So my runnable entry exit variable in which I am writing a unique value at the entry and exit is always 0. Then the second one is used for tasks. Third one is used for your ISRs, OS ISRs, and this data comparator is used for the I counter, which is a global variable. Now you need to enable this ITM, and then you need to press OK. Now you need to go to the profiler. So you have to select here data. You need to select OS object as usual, task and ISR. And in data area, you need to add the runnables, I mean the variable used for runnables and the I counter. So let's have a look. I mean you can add it by clicking on new, so new and trace, and then you can add it like this. So already I have added, so let's click on runnable. So you have to give a name runnable, and then if you click on this, then it will give you an option to look for the variable. So I have already selected, and then you need to select here interpretation as function entry exit identify by 0, and this is the define file which I'm using to define the unique IDs. So now let's click on OK, and similarly you need to add this I counter, but the interpretation here you need to use is regular variable. So now OK, then OK, my software is already running, and then I will run this. So here you see you have all the runnables here, you have all the tasks which you can see, you have ISRs, and this is the I counter. So this is the way you need to perform if you want to go for OS task ISR profiling or runnable profiling, or if you want to go for a data variable trace. So this is how you perform these things in SWO trace capture method. Now moving to the last slide of this presentation. This is about emulation adapter. What happens when you work with very less number pin devices, or you just have SWO and still you want to go for the full trace capabilities? Then the answer is such type of emulation adapter. In case of Traveo device, iSystem provides Traveo 1M or 2M emulation adapter, which is basically based on 176 pin Traveo device and provides full trace capability to 64, 80 or 100 pin device package. Definitely this emulation can be used as a standalone device, or when you do not have the board available on your desk. In that case you can order this emulation adapter and can be used for MCU evaluation or test purpose. So at this point I will end this webinar from my side, and I hope now you have a basic understanding of Cortex M4 architecture, trace architecture, or debug and trace features, and definitely how to use winIDEA for different use cases and to utilize those Cortex M4 debug and trace capabilities. So thank you.
Thank you, Manish, for your demonstration. So was very insightful. And now let's continue with the Q&A session. Several questions reached us. Are you ready, Manish?
Yeah, I'm ready.
Good. The first one is the DWT module has 4 hardware comparators. So ideally, we can trace 4 data variables. What is the possible solution when the use case is to trace more than 4 variables at a time?
Okay, so I would say, yeah, this is possible. But additional variables can be traced using the code instrumentation concept provided by the ITM. But the only one thing you have to take care here is like user must add code to the applications which writes content of the data variable to the so-called ITM stimulus ports. And once you do that, then ITM basically emits ITM trace messages with the containing data. So in this, using code instrumentation concept provided with the ITM, you can trace more than four variables at a time.
Thank you. Let's continue with the second one.
Mm-hmm.
In the parallel trace capture method, there is an option to select either 1-bit, 2-bit, or 4-bit. Which impact does this have on the trace bandwidth?
I mean, I would say this is a very good question because a user must know what exactly they have to use. So my answer is yes. This width selection basically in parallel trace capture method does have an impact on bandwidth and the trace data. And the interesting part is user can find it out by themselves, which selection is exactly required for them. So for better explanation, I will take an example like my example where I'm using S32K148 and which runs at 112 megahertz. So basically, if I consider in general a normal RISC architecture which has CPI, I mean clock per instruction is 1.6, then I would say my S32K148 controller can execute almost 112 megahertz divided by 1.6. This should be equal to almost 70 million instruction per cycle. And if I talk in terms of program flow, generated program flow trace data, then this would be equivalent to 70 megabits per second, or in terms of bytes, this will be 70 divided by 8, so equal to 9 megabytes per second. Now if I look at my trace clock, so basically it runs at half of the code frequency. So then it goes to 112 divided by 2, so almost 56 megahertz. And if you do the similar calculation, then you will find it out like with 1-bit selection you can handle up to 7 megabytes per second, and with 2-bit you can handle 14 megabytes per second, and with 4-bit you can handle up to 28 megabytes per second. So in my case, if I select 1-bit, then I get an overflow error because expected is 9 megabytes per second and 1-bit can handle only up to 7 megabytes per second. So definitely it's very, very, very critical information that user must have what exactly they need. And the advantage of this is they can use these information in their hardware design implementation also. So yeah, this is a very good question, and user must know what exactly they want and what they have to use.
Okay, and for all who were not able to follow all the calculations in your example, the webinar today will be recorded and you can find it on the YouTube channel in a few days.
Yeah, definitely. But I mean, like, you have to know at what frequency your core is running, and then based on that, you do all the math. It's so just pretty basic math, I would say.
That's a nice summary. Thank you. Let's go for a last question. Do the DWT comparators also allow to enable data trace for a specific address range, for example, covering an entire data array?
So it's a bit tricky question. It is like, I mean, my answer is no, not really, because the comparators which we have on Cortex-M4 actually can only compare against a single address. So yeah, it's not exactly you can cover the entire data array, but we do have an option. Like the option is this comparator allows us to mask the certain address LSBs, and then using that you can create address range. But however, the problem is these address range are always aligned to the mask LSBs. Okay, and this address range will not match with your exact address range of the data variable which you are going to trace. So in this situation, my answer is not really. You can, I mean, use this as an to covering an entire data range actually. But apart from that, here I would like to throw some information about Cortex M7. So if I talk about Traveo 8M device and all, so there also we have Cortex M7. So many users use that. So there also the same concept applies. But the implementation of Cortex M7 on higher SoCs, like higher end SoCs like S32G, there you have an comparator, and you can use that as a support of address range comparators, I would say. Yeah.
Okay. Thank you again, Manish. Let's come to an end of this webinar. Questions which were not answered now will be answered by email shortly.
Yeah, sure.
And before you leave, I would like to give you some additional information. Don't forget to download the presentation in the handout tab of the menu bar. Check out our free online trace tutorial and the YouTube channel where this webinar will be hosted, and others are already available. And if you want to, feel free to register for our newsletter to get interesting updates automatically. If questions come to your mind later, feel free to send an email to webinar@isystem.com. We'd like to say thank you for attending, and please fill in the feedback form after leaving. Bye and take care.